Today we are going to talk about how do we read information. Okay, most of the concepts related to reading we have already learnt. So, today I will just briefly go through, will not spend much time here, and the theory also I am not very confident. So, I will just briefly show you a lead, then all of you can read the papers to understand the theory better. Okay. I will highlight the technical aspect, what are the challenges when we try to implement in the industry and so on. Okay, so we have been learning about how do we write information, how do we store information. When it comes to reading the information from MRAM, the magnetoresistance is the one that determines how do we read information. Okay. So, we have already seen this many times. So, we are okay. Let us skip this one. So, we learned that there are three types of magnetoresistance: AMR, GMR and TMR. AMR is typically 2%, and I told you TMR in the industry can be around 200%. And if you look at GMR, for most practical purposes, GMR is only around 10%. Okay, so when you send a current through a GMR device, let us say you have a free layer, copper, some reference layer, you send a current to read the two resistance states of GMR device. Let us suppose the parallel configuration gives rise to 100 ohms, okay, and the anti-parallel configuration gives rise to 110 ohms. Okay, so, this is the 10%, right. So, 10% GMR means the two resistance will be different by about 10%. Okay. So, anti-parallel, let us say it gives 110 ohms, parallel gives 100 ohms, and you send a current of 100 microampere to convert this current into voltage. Then you will get like 10 millivolt and 11 millivolt. Okay. So, this is the difference between say bit 0 and bit 1. Okay, this 1 millivolt difference is too difficult to read. Okay. So, because of this reason people do not use GMR, they go for TMR, which gives rise to 200% tunneling magnetoresistance. So, as we learned before, tunneling magnetoresistance has a long history. Even though it was observed in 1970s at around 4 Kelvin, in 1990s people observed TMR at room temperature. Okay. This scientist from MIT and the scientist from Tohoku University came up with the TMR observation. So, at this point of time the tunneling magnetoresistance was only around 12-13% kind of thing. Okay. But it was exciting for the hard disk industry, because hard disk industry was already working on GMR, and there was hope to increase the TMR to even better values, so that we can read the information in a better way. So, again hard disk industry is the one that made the TMR progress first. Okay. So, if you look at the progress of the tunneling magnetoresistance as a function of year. So, you will see two regions. Okay. So, in one region the tunneling magnetoresistance grows like steadily. Then there is a region where the tunneling magnetoresistance has a huge jump. Okay. So, these are because of two types of physics and two types of material. Okay. So, in this region 1994 to 2004, people were looking at amorphous material as the barrier layer, tunnel barrier layer. Then somewhere in 2004, people started using crystalline material, crystalline barrier. Okay. So, here it is aluminum oxide. Here when it comes to this point, it is magnesium oxide barrier. Okay. So, this discovery, a theoretical proposal of magnesium oxide led to a larger TMR in the later part. Okay. Okay, again this is the definition of TMR. So, let us say you have certain resistance in the antiparallel state, certain resistance in the parallel state. So, the difference divided by the resistance of the parallel state gives rise to TMR. Let us say TMR is 200%. Okay, so, this is currently widely used in the industry. Okay, so, if the parallel state gives rise to 100 ohms, okay, then antiparallel state will be around 3000 ohm. Okay, that gives rise to 200% change. Okay, now you send the same current which I showed you before. Now you have a free layer, magnesium oxide, reference layer. So, you send a current of 100 milliampere. Okay. So, if you calculate the voltages and the difference, now the voltage difference will be around 0.2 volt. Okay. So, this 0.2 volt is enough to sense 0 and 1. So, if you remember the GMR example, the difference was only like 1 millivolt. Okay. Now, it is like 200 millivolt. Okay. So, you can 1 millivolt or 10 millivolt, but now you have 200 millivolt, which is enough to sense 1 and 0. Okay. So, because of this reason, people do not use AMR or GMR, people use magnesium oxide as the barrier, which can give rise to 200% TMR for reading information in MRAM. Okay, so, here the difference is only 1 millivolt, which is not enough. So, we need a signal swing of 0.2 volt. Okay. Signal swing means low resistance state gives certain voltage, high resistance gives certain voltage. So, this difference in the voltage has to be at least 0.2 volt. Okay, that is possible with this magnesium oxide. Okay, so, if you look at the history, so for many years until 2003, people were working on amorphous aluminum oxide, improving the property of aluminum oxide by various processings. So, they could go all the way to maybe 60% TMR. So, the first paper reported around 12 or 13% TMR. So, from here all the way they could go to 60%, slowly improving the processes, but they could not go beyond. Then a breakthrough came in 2004, where a group from Japan came up with 84% TMR. Then Stuart Parkin, he came up with 220% TMR. Then the same group in Japan, they came up with 230% TMR and so on. Okay. So, the 2004 is the onset, where the magnesium oxide made a breakthrough. Okay, so after that people did some research. So in the laboratory we can have 600 to 1000% TMR, but as I mentioned, in the industry they can achieve 200% TMR reasonably well. Okay. Okay, so I told you that there are two regions of TMR. So in one region people used So I told you in one region people used aluminum oxide, in another region people used magnesium oxide. Okay, so the theory behind aluminum oxide kind of a tunnel barrier can be explained using Julian model. So we briefly saw this during our TMR sensor theory part. Okay. So in the case of magnetic tunnel junction, we have two ferromagnetic layers. So their magnetization can be parallel or anti-parallel, and we have a tunnel barrier. Okay, so in this case we just ignore the the tunnel barrier. So it can be aluminum oxide or anything. So Julian model is independent of the tunnel barrier. So the TMR the TMR value that we get in Julian model depends only on the ferromagnetic layers 1 and 2. Okay. So let us say this is ferromagnetic layer 1, this is ferromagnetic layer 2. In Julian model, the TMR depends only on these two ferromagnetic layers, it does not discuss about the tunnel barrier. So that is a drawback of this model. Okay, so in this case the density of states on the left side ferromagnet and the right side ferromagnet. Okay. So the majority electrons in the left side and right side ferromagnets, and the minority electrons in the left side and the right side ferromagnet. For this parallel configuration is the first term. Okay. So Gp is these two terms. Okay, then there is a tunneling of electron when the two magnetization are anti-parallel. So that is given by these two terms. So the density of states in the left side and the density of states of, we are talking about. So when we say this, okay, this is N L up, this is N L down. Okay. Then here okay, so this is the terminology. Okay, so the electrons going from this side to this side, or this side to the other side, this to this, this to that. So we include all the terms there. So that gives rise to the TMR. So finally, if you look at this model, it will only talk about the polarization of the left electrode. For example, let us say this is ferromagnetic 1. So the polarization of the ferromagnetic layer 1 and the polarization of the ferromagnetic layer 2, only they determine the tunneling magnetoresistance. The barrier does not come into picture. Okay, so the definition of polarization is given here. So let us say we talk about only one ferromagnetic layer, let us erase this one. Okay, so polarization is basically the density of states of the majority electrons minus the density of states of the minority electrons divided by the total, that is basically the density of states. So, TMR will be only decided by the ferromagnetic layer. Okay. So, this model will not work all the time. For example, if you are studying aluminum oxide, so aluminum oxide or some hafnium oxide or some oxide as your variable. Let us say you have two ferromagnetic layers, identical ferromagnetic layer. But if you are inserting various oxides, for example, aluminum oxide, hafnium oxide, some titanium oxide whatsoever, right. You are studying the different oxides and measuring the TMR, then you cannot use Julian model to explain your result, okay, because Julian model ignores the barrier layer. So, it only considers the probability for electrons to tunnel from one side to the other side based on the ferromagnetic density of states. Okay. So, this model explains TMR only based on the ferromagnetic layer properties, it ignores the barrier layer property. Okay. So, if you look at some results like this, so here it is talking about polarization of the left side electrode, right side electrode and so on. So, if you make both the ferromagnetic layers to have a large polarization, you will have large TMR. Okay. So, that is basically the model. So, it does not talk about the role of a barrier layer in TMR. Okay. So, if you are studying the barrier layer effect on TMR, you cannot use this model. Okay. Then somewhere around 2000, this Professor Butler came up with another model based on first principle calculations, not just model. Okay. He proposed that if you are, instead of using aluminum oxide, if you make magnetic tunnel junction based on something like this iron, magnesium oxide iron in a particular crystal structure like 001, you can achieve very large TMR. I think according to this model, the TMR can be like 10,000% or even larger, something like that. Okay. So, this is one example where theory comes first, experiment comes later. So, you all know that the theory for laser was given by Einstein. Okay. So, Einstein came up with the theory of laser somewhere in 1920s, but it took around 30-40 years to experimentally realize laser. So, in a similar sense, this is a very useful theory which predicted that you can make magnetic tunnel junction with high TMR if you follow what this model suggests. Okay. So, in this case, this is Professor Butler, he carried out first principle simulations. I do not know, some of you may be doing density functional theory, those kind of things. So, he uses those kind of theory, and he say that electrons in certain band, particularly this delta 1 band, can tunnel through the magnesium oxide barrier more easily than the electrons in the other band. So, if you consider the tunneling for parallel case and anti-parallel case, there will be a huge difference. Okay. So, which can lead to a high tunneling magnetoresistance. Okay. So, this is what he predicted. There is a very nice paper. So, if you are very interested in the theory, you can go through the paper, I can pass to you later. Okay. So, in this paper he is using magnesium oxide with the crystal structure. So, if you consider the aluminum oxide is amorphous, whereas The material Professor Butler studied in his paper is magnesium oxide, which is crystalline. Okay. So, magnesium oxide has certain crystal structure. So, these blue atoms are magnesium and the red atoms are oxygen. Okay. So, they are arranged in certain way and there are several crystal directions. So, when we learnt about crystal, I told you that depending on which way you look at, you can have various crystal planes, crystal direction and so on. Okay. So, here again depending on how you look at, you can have like 111 or 001, 110 and things like that. Okay, so, in this case, for example, these are the delta band directions and these are the directions where the probability for electrons to tunnel from one ion layer to the other side of the magnesium, another ion layer. The probability for electron to tunnel from this side to the other side when the two magnetization are parallel is higher through this delta band. Okay. So, that is what he proposed. Okay. So, they look at various symmetries. Let me jump through many slides. Okay, now let us come here. So, here we are talking about layer number. For example, this side represents ion layer, one side of the magnetic tunnel junction, and from here onwards it is again ion, the other side of the magnetic tunnel junction, and this region represents the magnesium oxide layer. And this picture shows the density of states for parallel configuration. Okay, so, if the difference in the density of states is not much, okay, then we can say that the band matches and the probability for electron to tunnel from this side to the other side is higher. Okay. So, if say for example, this band does not match, okay, here there is a large mismatch and so on. So, this means tunneling probability is less and here may be almost impossible. Okay. So, he calculates the density of states for various configuration. So, here is like the majority electron, this is for minority electrons to go through the parallel state. So, all these things he looks at and he says that for this particular delta 1 band, the band matching is very good. So, the electron tunneling probability is very high. Okay, so, if you look at the anti-parallel configuration, the spin up electron can go reasonably okay, but the spin down electron cannot go. Okay. Okay, so, based on all these calculations, let me skip this one.
Sir, what's K parallel equal to 0?
What is 0?
K parallel, the third one.
K parallel is equal to 0. Actually, I do not remember this one, that is why I skipped this slide. So, the most important point is when you have this kind of crystal structure, the probability for electrons to tunnel, especially through the delta 1 band, is higher and we will have the low resistance state. And when you have anti-parallel, the probability for electrons to tunnel is less, so we will have high resistance. And the key difference between the aluminum oxide and magnesium oxide is that this low resistance of the magnesium oxide is actually much lower than aluminum oxide. Okay. Let us say in magnesium oxide you have like 3000 ohms versus 1000 ohms. In the case of aluminum oxide, you will go from 3000 ohms to probably like 2200 ohms, something like this. Okay. So, for parallel state you will have much lower resistance in magnesium oxide. So, that is the key result, and that is observed only when you have grown magnesium oxide in BCC 001 texture. Okay. So, this crystalline texture is important. So, all the calculations that I showed you before are based on the magnesium oxide in the 001 texture. Okay. Okay, so now I will show you some experimental results to show that the magnesium oxide 001 is important. Okay, so in this table you will see various compositions of the reference layer and various compositions of the free layer and the TMR of the structures. Okay. So, normally when you have cobalt, only cobalt can exist in HCP or FCC kind of structure, and iron is BCC. Okay, let us say you have an alloy which is 100% cobalt and 100% iron. So, you vary the cobalt and iron when you go from left to right. For example, let us say this is a cobalt 50, iron 50, something like this. Okay, so, depending on the relative composition, there will be some region where when the iron is lower, let us say cobalt is 85, iron is only 15. Until this region, this will be FCC, and beyond this region we will have BCC. Okay. So, depending on the ratio of cobalt and iron, you may end up having BCC structure or FCC structure. Okay. So, if you look at this table, here iron is less, 10% only. Okay. So, 10% iron is here. So, this is FCC, and in this case again cobalt iron is 10, iron is 10. I do not know, can you see from back? If you cannot see the letters, I can duplicate this slide. Okay, so this is BCC. Sorry, this is the FCC, this is the FCC, and so on. Okay. So, you will notice that when at least one of the layers is FCC, the TMR is very low, around 75, 50, something like that. On the other hand, when you have like cobalt 40, iron 40, both are BCC, then the TMR values are larger. Okay, so, this is what the theory predicted. I mean the theory actually proposed. The theory proposed that you should use magnesium oxide with a BCC 001 texture between two layers of iron to get high TMR. Okay, people do not use only iron, they mix with cobalt to have certain other additional properties. So, because of that now we can get like very large TMR. Okay. So, in all these cases it's having BCC. Okay. So, when both sides have BCC structure, you will have high TMR. When at least one side has FCC, you will have low TMR. Okay, that is what is shown here. So, this is another demonstration of the effect of having magnesium oxide in 001 or say in some other phase. Okay. So, here magnesium oxide is in 001, which agrees with what Professor Butler proposed, okay. But this is not the one he proposed. Okay. So, here magnesium oxide is in 111 phase. So, if you compare the TMR, this sample gave rise to high TMR, this sample gave rise to low TMR. Okay. So, this is the reason I told you earlier that if you have cobalt platinum multilayers, let us say you grow cobalt platinum multilayers. So, typically this cobalt platinum multilayer grows in FCC 111 structure. Okay. So, this FCC 111 is not preferred, okay, because it will give rise to low TMR. So, if you remember a few days ago I showed you the whole stack of MRAM. So, there is a cobalt platinum at the bottom, there is a cobalt platinum at the top, and this was the synthetic antiferromagnetic structure. Then on top of this we have magnesium oxide and the free layer. Okay, so, at the interface I showed you that there is a cobalt iron boron. Okay. You can look at the slides later, but this is something I showed you before. I did not tell you the reason why we have this cobalt iron, because that time it was too early to discuss that. Okay, so, the reason we have the cobalt iron here is to break the crystal structure following. Okay. So, if this cobalt platinum is FCC 111, okay. So, if this is FCC 111, if you grow this magnesium oxide directly on top of this, then magnesium oxide will grow in this 111 texture, then you will have low TMR. Okay. So, we do not want this one. So, to break that we insert an amorphous cobalt iron boron. So, now this is amorphous. So, on top of amorphous cobalt iron boron, magnesium oxide will grow with 001 texture. Okay. So, the TMR will not be affected because of this layer. So, when you grow materials, you have to think about what kind of crystal structures you are growing, whether this crystal structure will affect positively or negatively, you have to consider all these aspects. Okay, so, cobalt platinum multilayer is a good material for reference layer, because it has a large anisotropy constant. This will be stable even when you read or write information, but this has a problem of this FCC 111 texture, which can kill the tunneling magnetoresistance. So, to overcome this problem, people insert amorphous cobalt iron boron near the magnesium oxide interface. Okay, so, what people do is they deposit magnesium oxide on top of amorphous cobalt iron boron, and after every deposition is done, they will finally carry out some annealing at around 300 degrees Celsius for 1 hour. So, during that annealing, boron will go somewhere else, and this cobalt and boron will crystallize into cobalt ion 001 phase. Okay. So, this is what I mean, this boron will go away, finally you will have cobalt ion 001 phase. Okay. So, this is the procedure followed in the industry. So, for the industry production, there are two types of magnesium oxide deposition. One method is to have a magnesium oxide target, okay, and use radio frequency sputtering to get magnesium oxide layer. The second type is to use magnesium target. Magnesium is metal, okay, so you can use direct current sputtering. So, during the sputtering, they will deposit a thin layer of magnesium, then oxidize the magnesium to form magnesium oxide. Okay, so this is the reason I told you yesterday that in the industry there will be many chambers. There will be one chamber to deposit metals, another chamber for magnesium oxide. So, they will use oxygen gas to oxidize magnesium to form magnesium oxide. So, they do not want this oxygen to contaminate all the other materials like ruthenium, cobalt and boron, all these things. Okay. So, usually oxide chamber is separate. Okay, so, as I mentioned, if you have materials with the FCC11 texture, it is not good. So, we have to break this FCC111 or BCC111 texture, but we should focus on getting BCC001 crystal structure. Okay, that is important. So, what are the challenges for industry? So, one challenge is the tunnel barrier quality. So, we are depositing 1 nanometer of magnesium over a wafer that has a diameter of 30 centimeter. Imagine you need to deposit 1 nanometer MgO. So, throughout this 30 centimeter, your magnesium oxide thickness has to be uniform. Okay. So, if it is just say even plus or minus 0.2 nanometer, okay, then the TMR of the device that you make here will be say 100%, and the TMR of the device that you make here may be like 250%. Okay, so there will be huge changes in the tunneling resistance. So, we need to ensure that this thickness is uniform throughout the 300 nanometer, 30 centimeter wafer. So, this is a challenge, but industry is managing. So, this is where the sputtering is superior. So, many of you guys may be using PLD or some other form of technique to deposit films, but they are not as good as sputtering. Okay. Sputtering is the one that is industry friendly, that can make practical devices. If you do MBE, for example, MBE may be very good in achieving a very good crystal structure, but MBE is not useful in the industry. So, sputtering is the best technique. Okay, let's do some question and go for tea. Okay, majority of you are right. Tunneling magnetoresistance. So it's a T for tunneling. So this should be the answer. I don't know why two of you are choosing this. Okay, next one. Okay, these five are not following what I am talking about. Okay, I said many times that in the Julian model the barrier is not considered. The TMR is decided only by the ferromagnetic layers at the two sides. It's a very simple question. Okay, next one. Okay, most of you are right. Very good. Okay, next question is related to these three pictures. Which of these following MTJs will have the largest TMR? So we have two ferromagnetic materials. They are in different crystal structures in like BCC, FCC. Okay, most of you are right, okay, because you have listened to what I am talking about. So, I repeatedly mentioned, not once, maybe 3 or 5 times I mentioned that we need BCC structure materials for high TMR. Any FCC will kill the TMR. So, B and C have FCC, so B and C are not the correct answer, A is the correct answer. So, when you go to conference, you cannot learn much, because the conference, the speaker does not repeat, okay? He just goes with the flow, he tells only one thing, only one time. So, if you listen attentively, you may learn what the speaker talks about, but when it comes to classroom teaching like this, I repeat things many times. So, we are not attentive all the time, right. So, sometimes we may lose focus, but I repeat 3 or 4 times. I also do a recap, so that at least 1 out of these 5 times you will listen and understand. Okay. Okay, next one. Here you type yes, type yes. Okay, if I do not see all correct answers here, I will have heart attack. Okay. You saved my life. Go for a break, then we will come back and learn some domain wall memory concepts.